Yeah, thank you, organizers, as well. This is really, if I had, we're looking for transits around Earth-like transits around a sun-like star. After that introduction right now, I would be scared. Some of the spatial inhomogeneities that the sun has, that Svetlana was showing, would have me really saying the sun changes so much, it's so dynamic, you can't possibly do this. So let's look at the real sun, solar transits, looking for Earth-like planets going around sun stars. I crossed out the like here because I really am looking at the sun. There are a lot of sun-like stars, somewhere between 1 and several thousand sun-like stars that we know of, but we do know we at least have one. Let's look at it as a star. The sun has limb darkening. This is integrated up spatially and spectrally, limb darkening in the plot shown on the left side, and an Earth-like transit. Half of them roughly take between 10 and 13 hours or so to go across the sun. So this is a real Earth going across a real sun. These are simulations that you've all done. We're looking for things kind of on the period time of 10 hours or so. Here are measurements that we have of the sun from the last 40 years. These are spatially and spectrally integrated total solar irradiance measurements from space. These are radiometric measurements. Unlike what you typically do with stars, these are more than photometric, they're radiometric. They have good absolute precision. The photometric precision of these measurements, and incidentally, we do have overlap from the last 42 years here that let us put everything together into one composite. But being photometric, the photometric precision of some of the better instruments here are down in the 4 part per million range. So incredibly good photometric sensitivities and stabilities that are about 10 parts per million per year. So these are not instruments that you have to give up on after 90 days or 2 weeks because they've drifted too much. They're incredibly stable for long periods of time. I know that's not incredibly relevant when you're looking for 10-hour period transits, but still, these are the best radiometric instruments that have ever been flown. Here's a record from one such instrument going for about 17 years of the total solar irradiance. The variability you see in here, the ups and downs in the signal, those are from passages, formations, decay of active regions on the sun. It's not instrument noise. There's an 11-year solar cycle that you can see in this time series. On short time scales, you do see a lot of variability from sunspots forming, passing across the sun. The dips are from sunspots, brightenings are from faculae. So let's look at how variable the sun really is. Let's take a couple of months shown in blue here and expand it. This is an innocuous couple of months, nothing particularly exciting about this time, fairly typical. On that couple of month time scale, there's a solar rotation, 27-day period, where you do see variability, increases, decreases in the intensity, or in this case, the TSI. Let's look at typical 14 days, shown in blue again, and look at how variable things are there, going to a bit higher cadence measurements. So now that I've gone to higher cadence, you see the gradual decay that you saw on the last plot, but you also see a lot of high frequency variability. The sun is changing at small levels. These are kind of 100 part per million levels all the time on 5 to 10 minute time scales. What I should point out is an Earth-type transit would be about a 80 part per million decrease in the intensity of the sun, lasting for 10 hours, like I showed in that first slide. So you're looking for something, if you're looking for an Earth that's on the order of 80 parts per million, on top of a sun that's moving around at the 50 to 100 part per million level all the time. Let's take one day here and look at that one day, blow it up. Now this is from a spacecraft in low Earth orbit, so it does have omissions in data from when it's occulted by the Earth itself. But even then, you can see variability on the 100 part per million level going on all the time. Let's look at just a couple of orbits, so 3 hours worth of data. And again, on these 5 to 10 minute time scales, variability of 50 to 100 parts per million. On top of which you want to try to find, a 80 part per million decrease in the intensity as a planet goes across the sun. So it seems frighteningly difficult to do. And these are some studies, not these data, but studies I did prior actually to the launch of Kepler, wondering how feasible this would be. The spacecraft I'm looking at data from here have actually seen several transits, 4 from Mercury and 2 from Venus. Shown in yellow are the expected decreases that you would see from those transits. Venus is easy, it's pretty close to the Earth. When it transits, it looks pretty big. It's about a 1,000 part per million decrease. Mercury is much closer to what the Earth would be like when viewed from another solar system going across the sun. It's 40 parts per million, so half of what an Earth transit would be. So let's see what those look like. Venus, like I said, that's easy. 1,000 parts per million on top of a sun. The red points here are real data from the sun. And again, the variability you see is 100 parts per million or so, that the sun is changing all the time. The gray curve is a modeled curve, including limb darkening and the position of the spacecraft, the planet, the sun. The model, thank you. The model fits the data fairly well. That's easy to see. And if I look at these longer time scales, here's the earlier Venus transit, and it's, a typical sunspot. That doesn't look that different. It doesn't last as long as sunspots. Now let's look at Mercury. This is a little more Earth-like. Mercury, 40 part per million decrease. The gray curve is what I would model up. The red are the real data. I know where to look right here, but I can't look at those data and say, there it is. Here's the next transit that we saw of Mercury. Suggestive that maybe there's something there, but not in that first orbit. So again, not something, even knowing where to look, that you would say, there's Mercury. This looks a little more promising, but still nothing that if you didn't know where to look would jump out at you. And even the last transit doesn't quite make sense in that the first and the last orbits here really didn't drop as much as you might have expected. Again, your eye can be drawn to where you should be looking, where you know this occurred, but still, these are difficult to see. And if you look at data at that level, but the reason it starts to be doable is if I say, find the planet transit in here, this is my 14-day record, you can see it. Yeah, what I've done here is I've simulated an Earth-type planet transit, and I've put it on top of the data that we have. And indeed, right here is where your eye would pull out. Something's going on right there that's a little unusual. Why can you see that? Why does that come out? Here's the data, by the way, without that simulated transit put in place. The reason you can see it is the sun varies on time scales other than planetary transit time scales, luckily. It varies on high frequencies, it varies on low frequencies. But it doesn't vary a whole bunch on these 10-hour time scales. And planets show up on the right side here in this periodogram, a place where the sun really doesn't have a lot of spectral power. Sasha has shown this a little bit more in this matching of data and simulations. Again, low power spectra portions of the curve is where planetary transits typically occur. So the reason you can see these is that while the sun can horrifically vary spatially and temporally, It does so on timescales, luckily, that are different from the transit timescales that we're interested in finding. We've had several workshops that have talked about similarities between the sun and sun-like stars and shown how similar some stars can be to the sun. So even though initially you might look at the sun and say, boy, it'd be awfully hard to find a transit across that disk with all the spatial inhomogeneities that the sun shows and the temporal inhomogeneities, it is actually, like we now know, very doable. So yes, transits occur on time scales where the sun has low variability. And if you simulate a transit on typical solar data, it pretty well jumps out when you see an 80 part per million or so Earth type transit. So luckily, we're not up against an impossible problem, even though stars and the sun can be very variable. Thanks.